Hi folks, Mr. Ackerman here. Thanks for watching. This is a little bit of a special edition of the video series. I'd like to address one of the questions in section 4.5 of the textbook being Physics 12 by Nelson. The question deals with elastic potential energy as well as gravitational potential energy and even kinetic energy. So it's a fairly involved question. It involves bungee jumping, and it's a great question. I really like doing it. Been doing it for many years now with the students, and sometimes what happens is a student comes up to you and is getting a different answer than the back of the book's answer, and you can't see any problem with the solution that the student's presenting, and so you start looking at what's going on. And today was one of those days. We found a little bit of an error in the question, which sometimes happens. Even the people writing the book and the teachers sometimes make mistakes, and I'd like to point this out to you, and while I'm doing it, just show you how the question is to be done. So let's have a look. It's question 10 on page 219, and here's how it goes. There's a bungee jumper, mass given, and this jumper is standing on a platform above a river, maybe like what you see in this video, in this image right here. Now it says the length of the unstretched cord. So this is important because if you've never been bungee jumping before, you might not realize until you actually fall down a certain amount, the cord, as you can see here, will be unstretched. So there's actually no elastic potential energy involved in the problem yet. The force constant of the bungee cord, which behaves like a spring, is 65.5 newtons per meter. The jumper falls from rest, and it says just touches the water with a speed of 0. The cord acts like an ideal spring. Use conservation of energy to determine the jumper's speed at a height 12.5 meters above the water on the first fall. So there's a lot going on in this question. I would always recommend reading the question at least 2 times, maybe 3, just to make sure you're not missing anything. And if it's something like bungee jumping that you've never done, you may have to go do additional research to see what that's all about. Maybe you should watch a YouTube video on it. But to keep things short, I'm going to assume you already know what bungee jumping is, and we're going to start the problem. So what I would recommend doing in the beginning is writing down absolutely everything you know. Let's imagine that this is the platform where the bungee jumper is starting from, and there he or she is. The mass is given as 64.5 kilos. Now, as we can see from bungee jumping and as we can see from the question, the length of the unstretched cord, 10.1 meters, this means that the jumper can actually fall a distance of about 10.1 meters before any stretching begins. So let's put that in there, 10.1 meters, and we can even write in no stretch to remind ourselves not to include elastic potential energy just yet. At this point, obviously, the person will be falling, looking something like this, and the cord, which was until then very lax, or very slack rather, will suddenly begin to stretch. Now, as the cord stretches, I'm sure you can imagine the person is going to begin feeling that tension and will therefore be experiencing an upward force called Fx, assuming this behaves like an ideal spring. However, the person is still experiencing gravity and is therefore probably still accelerating. It says the person gets to the water at the bottom with a speed of 0. So I'll put that in here try to draw a nice straight line here. I'll put that in here as a blue line. I'll write in water. And it said that the platform was 48 meters above the water, so let's put in a nice long arrow like that, showing 48.0 meters all the way down. It says that the person gets to the bottom with a speed of 0, so let's draw the person in near the bottom. I'll draw the person just over to the side here, okay? And the reason I'm doing that is because I want to keep each part of the fall, like this part of the fall, I want it to be clear so it's easy to see what's going on. And over here, where the rope has stretched down and is now quite tight, it doesn't have the same slack that it had over there. Here we've got speed equals 0. We can also write in that the height above the ground is 0 because the person is down here. I guess what I'm implying is that h equals 0 is where Eg will equal 0. Remember, you are allowed to set the 0 point for gravitational potential energy anywhere you want in the problem, and we often do it at the lowest point in the question. What they're actually asking is find the speed of the jumper when he's 12.5 meters above the water on the first fall. So while this would be where the jumper ends up if we allowed him to fall all the way, what we're really interested in is a point which I'm going to draw over here. So once again, I apologize for having drawn 3 people. There are not 3 people in this question. It's just that there's 3 positions, and I'd like to keep each one straight in my head. So let's call this the 12.5 meter above the ground point. Excuse me for 1 sec, folks. Okay, sorry, we're back there. This is the 12.5 meters. Oops. 12.5 meters above the ground. There we go. And of course the person is moving, and we don't know how fast, so we got a question mark there. Okay, so the problem is set up. There's 3 different places. Why have I drawn 3 different places? Because they ask you to use the law of conservation of energy. That's right here. And if you remember what the law of conservation of energy tells us, it says that you can compare energies in any question at any 2 different points. And as long as you make the total energy equal at any of those 2 points, you ought to be able to solve what's going on. So basically, what they're saying is the following. E total at the top is equal to E total at, let's call this the top here, let's call this point A, is equal to E total at the bottom, let's call this bottom there, and let's call this point, I don't know, call it point C, let's say. And therefore, whatever the E total is at C, this value is equal to that value, is equal to that value, is equal to this value. In a moment, we're going to solve this. I just got to add in a couple more things. The person, it didn't say actually they jumped. It said he falls from rest. So V equals 0 up here. What else can we write? By the time he's fallen 10.1 meters, he will have some speed in the downward direction going like this. And I think now we have a lot of our information and we're ready to go and solve this. So what I'm going to do, I need a new screen. So allow me to just do a little cut and paste job here. Okay, I'll paste that in there, but I'm going to make it really small just so we don't have to keep switching screens here. That should be good enough. Okay, let's get that out of there, delete. Perfect, and we're ready to go. So they're asking for the speed at point C, so it would be a good idea to write E total at point C equals E total at any other point in the problem. Now, you can choose the top, you can choose what I've called point A, you could choose the bottom. It's up to you. However, what you really want to make sure that you do is pick a point where you know a lot of information. For example, at this point here, we don't know the speed, so this might not be the best point to choose. At the top here, we do know the speed. We also know that the cord is not stretched. We also know that this guy is 48 meters above the ground. So let's start there. If you now look at what all of the energies are, you can complete this term. You can fill out this term with all the types of energy. Like E total at point C, what kind of energy have we got here? I'll draw in the bungee cord, which I forgot earlier. We've got a stretched bungee cord, so there's E elastic. The guy is moving, so we've got E kinetic. And he's above the ground, so we've got Eg. So we put in EE at point C plus EK at point C plus EG at point C. And now we compare that to the top. What's going on at the top? Well, EE is 0 at the top because the cord has not yet stretched. So I'll write it in here, but we're going to make it 0 in a moment. What about EK? Well, he's not moving, so EK is equal to 0 at the top. I'll write it in here, even though I'm going to make it 0 in a moment. And EG, well, he's high up above the ground, so EG is certainly not 0. However, these are. So we can go like that. Okay. Now, E elastic, the formula for that is a half kx squared. The formula for kinetic is a half mv squared. And the formula for gravitational is mgh. On this side, all we're left with is mgh. And we don't want to confuse this h with that h. So this is the h at point C, and this is the h at the top. Now let's look at the information that was given in the question. They gave you the k value, so we know this. They gave you the mass, so we know that, and we know that, and we know that. And of course, you know g is 9.8, and you know the g in there. Now, what is the height at the top? That's the 48 meters, so you know this. What is the height at point C? They told you 12.5 meters above the water. The x value is all that's left. Well, remember, the cord does not start stretching for the first 10.1, that should be a 10.1 meters. And now he's 12.5 meters above the ground, so we can figure out that the amount of stretch in here will be the total 48 meters minus the 10.1, where no stretching can occur, minus the 12.5, which is the height above the ground. That's going to give you your x, so really you do know this. That leaves you with just speed, which is what they want you to solve for, and so I'm going to leave it to you to get an answer here. If you solve for the speed here, I believe you get the book's answer. And that's what I've been doing all these years. But today a student came in and said that she got the wrong answer, and we couldn't find a problem with her solution. Here's how she did it. I'll just box this off, or draw a line here. What this student did was, instead of choosing the top for comparison, she said E total at C, she's going to compare it with the bottom down here, which was a logical enough place because look at all the nice things that happen. At C, we just have the same information as here. So I'm just going to copy that and paste it in here. And that's equal to E total at the bottom. What do we got at the bottom? We got E elastic for sure. That bungee cord is very stretched at the bottom. Is there E gravitational? Well, actually, being at the bottom, that is 0. And is there kinetic energy? Well, if you read the question, it says no, the bungee jumper comes to rest at the bottom. So this student who came to me today was doing just as much math as I had to do. She had 2 zeros on this side, just like I had 2 zeros up here. Anyway, I'm not going to take up too much more of your time. What I really want you to do is the following. Go and sub in for these numbers. What is the elastic going to be? Well, figure out, first of all, be careful that you know how much stretch there is at the bottom here. Remember, it's the full 48 meters minus the 10.1. So put that in. For the kinetic, that's what you're solving for. And, whoops, sorry, I apologize. This down here goes to, that is for this. My apologies there. Some of you were probably wondering if I'd lost my mind. The answer is only slightly. That's the x value that you're going to use in a half kx squared over here, right, for the amount of stretch at the bottom. And up here for EE at point C, and for EK at point C, and for EG at point C, you can do it the same way we did over here, because it's still point C, right? Anyway, solve for V, and guess what's going to happen? you won't get the same answer. This answer will not equal the book's answer. Do you know why? Pause the video and think about it for a moment. Okay, and you're back, and I'll let you off the hook. The reason why this happens is because the book made a little bit of an error. They said, let the speed be 0 at the bottom. Because if you've ever gone bungee jumping, that's usually what happens. You hit the water, and you stop, and you come back up. The book said v equals 0. But actually, this is impossible based on the way the question is set up. Do you know why it's impossible? I'll give you a hint. See if you can do a calculation that proves the speed cannot be 0 at the bottom here. Pause the video and give that a try. Okay, and you're back, and now I'll let you off the hook if you weren't able to prove this. Here's what you're going to do. Let's go back one more time. I'm just going to do a cut and paste job here. Okay, copy, and we're going to paste that in here, going to make it a little smaller. Okay, here's what you can do. Here's the answer. Here's the punchline. At the very beginning, what did we know for sure? E total at the top was for sure equal to EG plus 0 EK plus 0 EE. We know that for sure 100% because that's what bungee jumping looks like. You're high up, you're not moving, no kinetic, and your cord is not stretched. So find yourself a value for MGH where this is 48 meters. This is your total energy for sure in the question. Now if the law of conservation of energy is to be true, then this value must equal your total energy at every other point, including the bottom, right over here. Well, what's going on at the bottom? Have we got EG? No. By definition, when you're at the bottom, that's 0. Have you got EE? Absolutely. That cord is definitely stretched. It's stretched by 1/2 kx squared. How much is x? We've already talked about that. Figure out x at the bottom, remembering 10.1 meters, no stretching occurs. So figure out this value here. And then do this. Solve for EK. Is your EK 0? The answer is going to be no, which means your speed cannot equal 0. But you say, the book said so. Well, guess what? The book did something that we as teachers all do at one point or another. We give too much information, TMI. We overdetermine the system by giving conflicting information without even realizing it sometimes. So they were trying to be realistic. They made a mistake. I've done this before. It's not a huge deal. What is most important is that someone caught it, and hopefully you could too, and you used your critical thinking skills to prove that there was a mistake. All right? I hope that helps you to understand elastic potential energy and kinetic energy and gravitational energy transformations that can occur, as well as how to solve this problem, and also to get you to think for yourself and think in depth. So, thanks for watching, and I will see you guys later. Bye.